So we have a problem here in which we need to predict what the product is, or the major product. And in order to do that, we need to figure out what mechanism to use. So the first thing that we need to look at is, do we have a leaving group attached to the molecule? And O-mesylate is a good leaving group. The next thing that we need to look at, does that leaving group, is it attached to a sp3 hybridized carbon? And yes, it is. So this can lead, that acts as a good leaving group. The next thing is that carbon that's attached to the leaving group, what degree is it? And that would be a secondary. So, now that we know it's secondary, of the four mechanisms, which mechanisms is going to be on the table? Which ones can we think about? And for secondary, all four are possible. So on the table, we have SN1, E1, SN2, and E2. All possibilities. So now we need to go to the little chart here that I have below there and look at all the parameters and kind of figure out what would be the most likely mechanism. So the first thing that we do is look at the strength of the attacking species. And there's the attacking species. This would be our substrate. And that attacking species, if we draw it like this, that's another representation of it. That's just ethanol. And ethanol has two lone pairs on that oxygen atom. And so is it a strong attacking species or a weak? And remember, I've said generally, if we have a species that is neutral, it's weak. And if it has a negative charge, it's strong. And so we would consider that attacking species weak. And weak attacking species favor SN1 and E1. Now the ethanol right there can act as a nucleophile. And when I say nucleophile, that would be a substitution reaction, so SN1. And then it can also be a base, which it's a weak base, so that would have to be E1 for acting as a base. Now, what about the concentration of the attacking species? There's no indication that it's dilute, and so that would favor SN2 and E2 because it has a high concentration. The leaving group right here is a really, really, really good leaving group. So that's going to favor SN1 and E1. Now the solvent. This one's interesting in the fact that the attacking species is also the solvent. Now ethanol is a liquid at room temperature, and so we have a liquid that's the solvent, and it's the attacking species. So in ethanol, can that molecule hydrogen bond? Yes, it can, because it has an oxygen with a hydrogen attached. So that molecule right there can hydrogen bond, so that makes that polar protic. And polar protic favors SN1 and E1. And so now we just sum it up. There's 3, 1, 3, and 1. And now we have a tie between SN1 and E1. So what would be how would you break the tie? The way I like to look at it, and other people like to look at it, is when there's a tie, you come in and factor in heat. If there's no heat displayed on the reaction scheme, then you favor substitution reactions. But if there's heat, then you favor elimination. So one way that it will be shown if there's heat or not is by words. They could say, and heat. Or if they don't do that, they'll do a delta symbol, which is just a triangle. like this. They draw a triangle, the delta symbol, and the delta symbol implies heat is being added. But since there is no heat being added, we are going to break the tie and say that our SN1 is the mechanism that wins out. Now the issue is when you come to the textbook here and zoom in on this one right here, the table, there is a slight discrepancy. So if you go back to the molecule that we're looking at, what degree is it? Secondary. And then the attacking species, we described it as a weak nucleophile or weak base. So when you take a look at that, okay, right here, it kind of has this X right here. See, that doesn't make any sense, because that reaction can still occur. So honestly, I don't know why the textbook even says that. And so that's probably not the best example to use that table. So we'll just come back to how I've been teaching it to you right here. And so in class, I'll show you a different example where we can use that table and it will make more sense. So let's actually kind of forget I even showed you that table, and let's just stick with this. Okay, so I said it's going to be an SN1. So now that we know it's an SN1, we can now perform the mechanism in order to predict the product. So I'm going to redraw the substrate. O-mesylate, and then we have our dashed methyl right there. So we said it is a SN1, so that means the leaving group has to leave first. And so our molecule gives us a secondary carbocation, and plus our O-mesylate, that will be negatively charged, that's floating around. And now our solvent slash nucleophile, there's our ethanol. That ethanol could, in theory, come in and attack from the top face. If it attacks from the top face, we would have a product that looks like this. OH. Or if it attacked from the bottom face, we would get this species right here. And then you could, in theory, not in theory, you would then do a proton transfer step in which you take a second ethanol molecule, and that will come in and do a proton transfer step to generate our product, which would look like this. And then you would have your ethanol with that extra proton there. You would do the same thing for this molecule here. That would come in, whoops, come in, grab that, do a proton transfer. So you would then, what functional group did I just make? There's an ether. Okay, so we would get a racemic mixture of those products right there. But hopefully you've already are in a little bit of shock saying, whoa, Dr. Lawrence, you made a mistake. And I did, because what have I said you're supposed to do when you generate a carbocation? I said, stop what you're doing. And when I say stop what you're doing, that's this step right here. Don't do that step yet. because you have to look at your carbocation intermediate and ask, can you do a rearrangement? And so what are you asking? You're looking at the carbon that the carbocation is attached. Go to the adjacent carbons. And on those adjacent carbons, I see that I have 3 hydrogens. Could we do a hydride shift with this green hydrogen? The answer is if you did, you would go from a secondary carbocation to a primary carbocation. And that's not increasing the stability of the carbocation. So that does not work. Is there a proton on that adjacent carbon? No, there's not. But you do have what? A methyl group. So our CH3 right there. So we could do a 1,2 methyl shift. And if we do that 1,2 methyl shift, our intermediate now looks like this. Okay, and then we have a plus charge there. And now our ethanol can then attack that guy on the front face. When that attacks on the front face, we would have something like that. Let's move that over there. It has to be positively charged. And then we would do a, just like we did with the other examples, do a proton transfer step in which that would come in, grab that proton to give us our final product here. Keep it consistent, I guess. We'll go okay, plus our ethanol that's been protonated. But remember, since that's a carbocation right here, this is a carbocation, that is sp2 hybridized. So the p orbitals, well, that carbocation is flat, so it can attack from the top face or the bottom face. So now let's look at the bottom face. What if that comes in the bottom face? Then we will have our structure that looks like this. Positively charged. We'll do a proton transfer step where the ethanol will come in and deprotonate that species to give us our product. Right there. And so, in order to make this look more accurate here, we would have to actually, because what did we just generate here? We generated a stereocenter. So we can't have 3 of those bonds in the same plane. So if I'm looking at this guy here, if the oxygen's coming in as a wedge, then that makes this guy the dash. And with the one below it, that would have to make this guy the wedge. So now we are showing the proper stereochemistry. And so these guys right here would be the major product. We would have a racemic mixture, those as the major product. And then these right here would be the minor product. So if this was a multiple choice question, then you're going to get all sorts of combinations with those 4 molecules there. So you would have answer choices like, is it just this molecule that's the product? Or is it both of these? Okay, so based off the mechanism, and you are generating this carbocation right here, you know you're going to get a racemic mixture. And so it's these guys in red, that's the major product. So I hope that is helpful to you. And as always, if you need any help, please reach out via the discussion forums. or come to my office hours. I'll be more than happy to walk through problems with you.